Afternoon all. My name is Richard Moar. I'm a control and instrument engineer based at Sullivan Oil Terminal in Shetland, and I'm about to share with you some information on our wireless gas detector project. First, some background and context to our site and its location. Sullivan Oil Terminal is located on the Shetland Islands, the most northerly part of the British Isles. So we're on 60 degrees latitude, which puts us in line with Anchorage in Alaska. Lots of daylight in the summer and not much in the winter, and not very high temperatures, a lot of wind and rain. The location of our terminal has been key to our success. We are ideally placed to service the northern North Sea fields, Brent and Ninian, and the west of Shetland fields, Foynhaven, Schiehallion and Clare. We're principally a storage terminal with minimal processing on site. Previously we had LPG storage. We now only have a fuel gas stream take-off for our on-site pump station. Constructed between 1975 and 1982, the workforce peaked at over 7,000 people, with a population of 17,500 people in Shetland in the early 70s. It was considerable impact to Ireland, so it was a big deal. The peak production of the site was over 1.5 million barrels a day during the mid-80s. At that time, we were also loading over 600 tankers per year. And the 25th of November 2018, we celebrated 40 years operation and had processed over 8 billion barrels of oil at that time. However, we're now operating approximately 10% of that as field production declines and plateaus. So, give you an overview of the problem that we had and the wireless gas detection that we installed. So we had additional gas detection required in our operational areas. That brought with it a number of challenges. Our site is very large; it's over 1,000 acres, but we also had a very short timescale to complete the work in, which is within 12 months. And then on top of that, we had COVID-19 throw a spanner into the works and try and push us back. To give you some context as to the picture that's on the screen here, the stars are the locations where we needed the gas detection at. There is a main road on our site, we call it Avenue A. It runs from about 11 o'clock on the picture down to about 4 o'clock. That's just over 1 mile long, about 1.8 kilometres. So in order to get all the detection installed around the site in an operational site, a brownfield site, we had a lot of cables to run, which was going to take a lot of time and cause a lot of delays and additional expense. So we have rationalised the plant in operation as time has gone on. That's why we only have stars in certain areas. But there's also further work ongoing to review the plant that we still require. So, in summary, if we were to design and install a typical hardwire fire and gas system, by the time we were commissioning it, we would be about to switch off the plant. Potentially, it was about to monitor. So, we needed to think outside the box and do something differently. So now for the technical bit, I was going to get my colleagues that are there present in the room to run through a couple of slides with you. Cybersecurity is at the forefront of what we do. We spend a lot of time securing and monitoring our systems. And I'll pass you across to Adney.
So my name's Dave Keane from Drager Safety. I helped design the system, and basically one of the biggest concerns was cybersecurity, so we needed to address common threats for wireless communication, which is data sniffing, replay or delay attacks, data falsification and data spoofing, but we still need to have the safety requirements for still response times and mean time between failures. Next slide. Oh, there we go.
moved on to ISA. The next slide, the ISA 100.
Yeah. Yeah, so obviously the ISA 100 protocol was built with safety in mind. So one of the key features is 128-bit encryption. As encryption is done on the device level, we needed to keep the encryption low to reduce basically the size of the data packets and the use of the power in the devices. So generally the devices will have a 2-year battery life, so we want to try and minimize any waste of power. Yes, so we chose 128 AES encryption. Generally, it's, in my opinion, is one of the safest encryption methods there is. It's small, and to brute force it and try and crack the encryption would take, the sun would burn out before it was even feasibly possible. There's no computers or systems on the planet which could crack it at the moment. People claim that quantum computers might do it, but we'll have to see. I'm not convinced. Next slide, please, Richard. Yeah, so here's some typical threats which would normally affect Wi-Fi or 802.11, but we have security elements in place to stop all attacks. So in some way or another, hacking can't occur, basically. So obviously we have data encryption to stop sniffing, device authentication. So we did manage to get hold of a Wi-Fi dongle, with, well, a wireless dongle which uses 802.15, which is the same as ISA 100. Yeah. But we could not sniff the data because the device we were using was not authenticated. So again, we struggled to try. We've tried to brute force this. We've tried a few hacks and nothing really works. The only thing that does work is radio jamming, but it's you need a lot of equipment, a lot of big equipment to even be remotely effective. All data is authenticated, so sniffing, replay attacks, they won't work, and also data spoofing. And then we have data freshness, so it's a completely secure protocol. We've had there's been a few white papers on people claiming they've managed to hack ISA 100, but they've been falsified. They weren't true. They've either used over-the-air provisioning where they've stole data as it was being transmitted, join keys, but we don't do that. We don't use over-the-air provisioning. We always use serial device, and we provision every device in a secure location, and nothing's shared. Next slide, please, Richard.
So just to say a
I
little
think
bit
it's back
about,
to me now, I think.
so I just wanted to talk about the safety level, and then you can take over. Tell him that No, not next slide. Just wait for. I will just let them go afterwards. So basically, for the safety reasons,
okay,
we are using ISA 100 because it was developed by end user input. So the first priority was security of the communication. But they're also an open protocol, so we can use it across the different members of ISA 100. We have multi-speed communication, so it's all monitored. So especially for our Seal 2 wireless gas detection, you need to ensure the package comes through at a deterministic time. So for our devices, we're using the time slots and the guaranteed response times of the network. Also, being able to tunnel other protocols. So especially today when we're talking about systems working together, ISA 100 is perfectly suited for that because we can put Modbus inside for some of the communications. You can use OPC UA inside ISA 100. But for safety applications, we are using Profinet ProfiSafe, which gives us a black channel that is wireless and gave us the possibility to get a Seal 2 certified wireless loop for safety systems. And also we're looking at scalability. When you install this equipment, you're not just getting a gas detection system, but you have scalability to incorporate inputs, outputs, temperature measurements, and it's all capable in the same system. And it's a global usability, which is important. And also we do ensure that the packages get through. It's all monitored by the gateways. So you can see that you have the signal strength, no packet data loss. And basically, we also do clear channel assessment on ISA 100. So if there's any of the sub-channels of the 2.4 gigahertz that are getting a lot of noise, the system automatically adapts and puts the information in the time slots and frequencies that are available. So it's safe and secure and addresses the safety critical equipment that we need. And especially for Solombo, we used redundant gateways. from Yokogawa, and they give us about 450 years mean time between failures. So normally we would say that we're slightly better than a cable on mean time between failures for the communication. Then he can start.
No problem. I'll just we'll move on to the next slide and discuss the solution. So the solution that we devised based on the locations where we needed detection was to install redundant gateways, as Adney just mentioned, in 5 locations where we would connect the detectors back to. So the project in numbers is we had 124 detectors we identified we required. This, in order to put that infrastructure in place, we also had a further 27 routers, 10 backbone routers to give us redundancy, and again 10 management stations for redundancy. Within the DCS itself that was displaying all this information, we ended up with a total of 1,384 DCS points. 854 of them were digital and 530 of them were analog, and we created 27 new DCS displays, a sample of which are coming up. So for each detector that we installed, 124, they each have 10 points, 7 status points and 3 analogs. And the reasons why we did that is on the slide. Minimize the cabling required. So in these 5 locations, we had spareage that we could utilize. We didn't have to run any bulk cables in any location. We had to do some minor cabling within buildings, but that wasn't going to be a problem. It was quick to do. Enabled fast deployment, and ultimately, if we had to change where the detections were or where we needed it, we could uplift it and move it and upscale it as well, as Adney says. So I've now just got a few photographs just to give you some samples of the detection that we installed, what they look like, give you a bit of context. The left-hand photograph is a pair of redundant routers on one of our extended stands. Before committing to the project, now that we were suspicious, we did a site survey of the locations that we need to fit the detectors and to confirm the connectivity and the reliability, etc. So in order to ensure rapid deployment, we then fabricated 3 different stands, a standard aerial, an extended aerial, and then an extended aerial. So this gave us the opportunity to put the antenna at a higher location in order to improve the connection back to the infrastructure and ensure we got a good signal for where we needed the detectors. In the following photo, you will see that our weather can be quite challenging. So it's nice and bright and sunny in these 2. So the photograph on the left is our routers, and then the one on the right is just a detector on an extended stand with the antenna, the white tip on the top of the yellow post there. And then so during the installation, we had a variety of weather. We had some sunny days, we had some cold days, we had some snowy days, we had some wet days. Again, these are just a quick sample of some of the detection within the plant area. Again, the left-hand photograph is a detector with an extended antenna. The middle photograph is an extended antenna, so it ends up being approximately 2 meters high at that point. And then on the right-hand side, that's it's the standard detector with a standard antenna within one of our tank bunds. And then just a few more photos. We even got some nice icicles on one of the days we were out on site one night. So. I've just got a slide to run through on the redundancy element of the project. This was key to us. Availability was key to us, and the system needed to be robust and reliable with no single point of failure. So every detector that is installed has a primary route and a secondary route configured. So in the event the primary fails, it will default across to the secondary route. So examples of this can be seen in the slide. So the solid line on both the left-hand display and the right-hand display is the primary route, and then the broken line is the secondary route. The right-hand image is just from the management station monitoring software. Just a screen capture of that. But as you can see, if any one piece of the jigsaw was to fall out, the detector would would reroute themselves through another available piece. Failure of the routing on any device will be alarmed on the DCS to operations for them to then raise a corrective work request. So, therefore, achieving our requirement of availability. This next slide is just a couple of quick screenshots of the detection that the DCS displays that we created for these detectors. As I mentioned earlier, there's 7 diagnostic alarms for each detector. That can be seen just down in the bottom right of this slide here, where the detector GDP2887W. So we've got the green status symbols there of the different status bits. There's actually 8. One on the top, gas detected, comes off. That's using the analog display to then fire that button. So there is 8 buttons there. The one on the top is fired from one of the 3 analog signals, which is percentage LEL, which is shown in the bar along the top, the white bar, which is 0, which is what we like to see, 0% LEL. And then the battery duration down at the bottom, 146. And then just below the battery symbol there, it says comms healthy. So the 3 analog indications we're using is the percentage LEL, remaining battery duration, and then the comms connectivity. So to recap on the benefits, successes. Perseverance was a key thread to this project. Day 1 of our site survey site survey and testing was interesting. We started in our crude storage tank farm. We started where we thought it was going to be easy. Large open spaces with no obstructions, but lots of concrete, which is in the lined buns of our storage tanks. And we established that acts as a very good sponge for the signals we were trying to capture. So me and my colleague Brian, who's since retired, when we went back to office, we really wondered what we were doing with this thing when we started. But there were just a number of challenges in that location. And we were able to identify those and address those and move on from there. We purchased additional equipment as part of our on-site commission spares, which that enabled us to have additional routers to improve connectivity where required when it came to actual final locations. So the site survey that we did was not 100%. We simply didn't have the time to do all that. So we did a large sample and took an estimate thereafter as to what we needed and made sure we had the flexibility to deliver what we needed. We had a collaborative approach and delivery. Both us, EnQuest, SVT, and Draeger challenged one another, and it was successful. We worked closely with Draeger to establish how the system worked and make clear what it needed to do. No single points of failure, security required, etc. And we achieved that. It proved challenging, and at times we had to revisit the engineering solution to achieve it. So there are some limitations within it that cannot tolerate a double routing failure. But we know that limitation, and an alarm raised as soon as the first routing failure comes in. So it's not undisclosed. But ultimately, we met the criteria and delivered a successful project. And we also had COVID-19 to deal with then, as well as now. Can't believe I'm not there, guys. I'm totally devastated. But so yeah, when it came to actually doing our factory acceptance testing, we had limited availability to do the testing. We were at the factory for initial testing, and thereafter we had to think outside the box and do some remote FAT testing, which was different, but it was successful. It enabled us to achieve what we needed to do. And then just a quick wrap up on the lessons learned. Flexibility was key. So the flexibility of the system, the flexibility of the vendors, and the teamwork that we achieved, we enabled us to achieve an optimized installation, both the placement and the connectivity. On the system side, what I have been doing is regular monitoring of the system, and daily there was no issues, and we need to continually just check in on things periodically. As we've owned and operated the system, we've learned to optimize and check and verify alarm settings, for example, battery levels and things like that. And we've had some weather challenges regarding the wind that we can experience on site and some of our thank funds and things. But it's been a collaborative approach, and it continues to be. So it's been successful. And that's all from me. Thank you.